Hello everyone, welcome to the chapter 3. So in today's chapter, we'll be looking into the conditions for the equilibrium of a particle. Then we will look into the free body diagram, and finally we'll look into the coplanar force systems. So today's objective, we will be able to draw the free body diagram. This might be appear in your exam. And we might be able to use the equations of equilibrium to solve a 2D problem. So let's move into today's lecture. So what are the conditions for the equilibrium of a particle? Let's look into that. A particle is said to be like at equilibrium if it's remained at rest or has a constant velocity, which is also stated in our Newton's law, right? So a particle has to be in equilibrium. So it has to be in rest or it should move in a constant velocity. There shouldn't be any acceleration. For that, we can use the equation that all the summation of the forces is equals to 0. Let's imagine the figure shown here. So we have this ball over here, and the forces acting on that is going to be what? F1, F2, and F3. So all these forces, the summation of all these vectors should be equal to 0 for this object to be equilibrium. Assume that it's not equal to 0 and it's in get some numbers of a resultant force. What happens? The ball is going to go in that particular direction. So for this force to be equilibrium, we know that all these forces summation should be equal to 0. We looked in the previous chapters how to get the addition of forces in a vector, Cartesian coordinate, or in scalar. So you should be able to get the addition of forces. So to maintain the equilibrium, it is always necessary to satisfy Newton's first law of motion. That's what we mentioned before. So let's look into this one requires the resultant force acting on any particle to be equal to 0. That's why the summation of all the forces, which is the resultant force, it's going to be 0 for the particle to be in equilibrium. So you should always remember that. Now let's move into the free body diagram. So the free body diagram, so to apply equilibrium, we must identify the knowns and the unknown forces that are acting on a particle. So this can be done by isolating the particle from its surrounding. This is what we call it as a free body diagram. So the classic example, we'll see a hanging weight. So let's say a hanging weight hanging from a rope. So we have the ball and it has a weight. So we know that the weight of the body has downwards, that everybody knows. So that's going to be downwards. That's our weight. It's not the mass, it's weight. That's why we put mass times mg to make it as a weight, as a force. Then because this is something from the spring, we know that spring is going to have some force. So that's going to be the 10 acting on a why it's marked as T. So these are the two forces that will be acting in my particle. So how did I draw my free body diagram? I just isolated particle and put all my own force. That is my weight. That's unknown force. That's my tension. So let's look into the procedure for drawing the diagram. So first we are going to outline the shape. And then we are going to show all the forces acting on the particle. Then you're going to identify each forces. So let's assume an example. We have a table and then we have a box on that top. So I'm going to draw the free body diagram of that box and the table combination. So I have the box and then I have the table. Then I know I'm going to take my box separately. I'm going to look into the forces acting on that. I know that box is resting on my table. I know that there will be a weight for my box, which is going to act downward. So that's going to be my mass times the gravitational acceleration. So that's in and because this is resting on this box, there's something reaction on my box from the table. So I'm going to draw my forces and then unknown forces. That's how we draw the free body diagram. These are for single systems. Let's look into another type of system, how we get the forces like cables and pulleys. How are we going to show our forces? So these cables will be always in tension. So we have tension forces T1 and T2 acting. So those are the two forces which are acting on my cable. So now I'm going to draw the first force acting on my T1. I'm going to separate that string cable apart. So I have a force T1 and then I know there should be an equal and opposite reaction acting on the other end. to keep this one in equilibrium. Then I'm going to draw my T2. Then I'll draw the T2, and I know that there's going to be another equal and opposite reaction acting. That's going to be T. And for this to be equilibrium, we know that the summation of the forces should be equal to 0. So this T1 plus T2 should be equal, and this should be equal for that to be equal. So we know that from this equation, we can say that the tension along this cable is going to be equal. So no matter what, when you have a cable attached, the tension acting on this is going to be equal for a cable in a pulley. So let's look into the coplanar force systems. Let's look into a 3D example which has a coplanar force system. So what are coplanar force systems? So we have a point A. So the A is attached over here. And then we have it is attached to points B and B, and then we have the weight downwards with the C, which is a 40 kilogram. So what do we do? So if this whole assembly is equal, that particle A also should. So to determine the forces that is acting on cables, given weight, you need to know how to body diagram. Then apply the equilibrium. So that's what we're going to be looking at here. So how are we going to use the body diagram? So why, what, how we do a frequent test? Let's see what is. So frequent diagram is a drawing which shows you all the experiments in the fund. So you get to know what are the forces acting. Why do we need this free body diagram? Able to write equations of system and use the solver. If any forces acting, let's see how do we do that. First, imagine they're going to isolate but they're separate. So imagine this A on as the same. Then you're going to show all the forces acting. First is going to be the active forces and forces they have. So in this case, 40 kilograms is particle down. Then you identify the active. That's going to resist. We have this cable speed. Before that, there is no so we're going to show all the unknown magnitude and direction. So let's look into the figure. First, the age of a then I know what is the because there is a cable, I know that's because of this going to be a sense. Both equal now. Pressing on it. So that I have the sensor. And because of C I have 4 vacuum downwards, 40 kilograms are getting then I know all the forces. So once I know the forces, I should be able to find out the unknown one. So since this particle to be, we know that the next also now, so we need to write all vectors or the C and D is equal to 0. So in general, if you know the particle equilibrium, components is going to be 0 and also that means all the if this is in equilibrium, then all the forces acting horizontal is 0. All the forces acting in the vertical direction are 0. So we know that in our vector add the forces. So we get write it like that, and then we equate it below the vector equation that forces is system is in equilibrium. Or we can write it in scalar form, just add the forces and then we get back to zero. So these are the two scalar equations of equilibrium we can use to solve for like two unknowns. So if you know the x direction forces, if you know the y direction forces, two unknowns, perfect to find. So let's look into the equations of 2D equilibrium. So now we have the cylinder and I know the free body diagram. So first I'm going to write the equations here like in scalar form in my horizontal direction. So this is where we are going to get what projection, or we are going to get the components in x and y direction. So that's what we were studying in all the classes. So this is x and y. That's the first what we studied in the second class. So that's very easy how to get the x and y component. If you have a force, we know that angle is given, we get cos and then the sine. So if I want to take in the x direction, I know this force FB is making 30 with my horizontal. So I know this FB cos 30 will give me the horizontal component, while the FB sin 30 is going to give me the vertical component. And FD is pretty much acting in the horizontal direction, so no vertical component. And FC is acting in my vertical direction, so there's no horizontal component. Perfect. So now I'll be writing my equations of equilibrium. So first I'm going to write it in the horizontal direction. So I have FB cos 30 and then I have minus FD in the opposite direction. Then the vertical one, so the vertical one we have FB sin 30 in positive direction, but FC is in the negative direction. Then I have two equations. So now I need to find FB and FD to say what are the forces that should act on my cable to keep my particle in equilibrium. So now I solve the FB. So I solve these simultaneous equations. Then I get FB as 785 Newton. Then I get FD as 680 Newton. You can ask how we solve that. So this you saw it's like simultaneous equation. You can directly plug it in calculator and get it, or else you can get the FB from here. So FB is going to be 392.4 divided by sine 30. Sine 30 is going to be half. So we can get FB. So once you find that value, you just go and substitute here. Then you will know what is FD. Okay, so now we have that. So we had two unknown forces, we had two equations, so we found the forces acting on the system. So we looked into cables and pulleys. So now we look some cables here. Now we're going to look into another type of system which is called simple spring. So we know spring. So it's going to be spring hanging away. When you apply a force or weight, what happened? The length is going to be stretched out. So you have the initial length and it's going to elongate. So we know that spring force is equals to the spring constant. Information of So we have that. So I know if I know the weight acting on that, I put mg. Then I know the force equation. So what do I do that? I know there is a spring force acting. That's my F. So I know the spring force acting should be equal to the weight or the force acting downwards for the spring to be continuous. So I get that instead of F, I put K times S. So I have that. So this should be in equilibrium for my spring to be in equilibrium. So I pretty much can get what is my spring constant, or you can get how much it has elongated using this equation if you know the spring constant. So what are the applications of this? Let's say a crane is lifting a load. So if you want to decide the shaft holding the load to the crane will fail, then you need to know what are the forces in the shaft. So how could you find that? You just separate the system where you have the weight and you know the tension acting on your strap, then you can find out what is the force that should be equal to the weight to get it. The other one is smooth contact. So we know that if an object is going to rest on a smooth surface, then the surface will exert a force on the object, which is going to be normal at the point of contact. In addition to this normal force, the cylinder is also subjected to its weight and the force in the cord, right? So since these three forces are concurrent at the center of the cylinder, we can apply the equation of your equilibrium of the particle, which is same as applying it to the cylinder. So we have the cylinder over here. So we know that it's on a smooth contact. So we know that there's going to be a reaction force. Because it is smooth surface, we're not considering any resistance. Sorry, we're not considering any friction force. So we have a normal force reaction and then the tension in the core, and we know the weight is acting down. So these are the three forces that will be acting on your particle. Let's look into an example one, which is a box which weighs 550 kg, and the geometry is shown here. A and also in the rows A, B, and is what you want to find. So we can draw the free body diagram for point A. Then you apply equation of equilibrium to solve it. So how do we do that? So I just remove my point A from all the systems. Then I know I have 1, 2, and 3 tension force cable forces acting. And I know the force acting on this rope is going to be this 550 pounds. So I get active. So let me draw my free body diagram. So I'm going to take my A and now FC tension, FB, and the weight acting downwards. This is similar to the one we looked like in before previous slides. Then I'm going to apply the equations of equilibrium. So let's see what are the equilibrium equations. So I have FC. I know the angle. So how do we get FC? Can you recall what we studied? Yeah, that's FC times 4 by 5. So now going to write that horizontally. Of that negative numbers, FC force right in the vertical direction. When I solve this to get my F, so it's just the magnitude here. This is scalar bar. So the magnitude is equal to h. Okay, that's one example. Let's look into the next one. So you have a mass which is 40 kilograms, and the tensions in the cable is like B and B. So they have to find out the tension. So what we have to do is you have to draw a free body diagram. Maybe you have to find where to draw the free body diagram is tricky. So they asked to find the tensions in TE, EA, and EB. So it's kind of joining. So you see where all these forces which they asked to find this joining is at E. So it's better to get the free body diagram at point. Then you apply the equations of equilibrium and then you solve and find the force. So let's draw the free body diagram. So take your time and pause the video and draw the free body diagram and compare it whether you did a good job.